Good day. Hi, I'm Criselda and my matrix number is 277604. Today, my group will be presenting about the introduction of electricity. So first of all, I would like to begin with the history of electricity. Electricity is one of the most important things that science has given to mankind. After 300 years of R&D, research and development in electricity, it has turned from a scientific interest into a daily necessity. Nowadays, electricity is an important living tool, but when did this journey actually begin? So let us see a short video about the history of electricity.
Electricity is one of the most important things that science has given to mankind. By nearly 300 years of research and development, electricity turned from a scientific interest into a daily necessity. Nowadays, electricity is one of the most important living tools. But when did this journey actually begin? And how did electricity become what it is today? Long before even anyone knew that electricity existed, people were aware of shocks from electric fish. Ancient Egyptian texts referred to this fish as the thunderer of the Nile and described them as the protectors of all other fish. Electric fish was also noted by ancient Greek, Roman, and Arabic naturalists and physicians. Some cultures knew that by rubbing things like amber rod with cat fur, lighter objects like feathers could be attracted. Greek philosopher Thales made a series of observations on static electricity around 600 BCE, from which he believed that friction rendered amber magnetic. Until 17th century, electricity was just an intellectual curiosity. In the year 1600, English scientist William Gilbert wrote *The Magnet*, in which he made a careful study of electricity and magnetism. For the first time, he used the Neo-Latin word electricus, which means like amber. This gave rise to the English words electric and electricity. Benjamin Franklin conducted extensive research in electricity. He even sold his possessions to fund his work. In June 1752, he attached a metal key with a wet kite string and flew the kite in a thunderstorm. Electric sparks in the metal key proved that lightning was indeed electrical in nature. The early 19th century was a period of rapid progress in electrical science. Discovery of Volta's battery gave scientists a more reliable source of electricity. After the recognition of electromagnetism, Michael Faraday invented the electric motor in 1821, and George Ohm mathematically analyzed the electrical circuit in 1827. Electricity, magnetism, and light were definitively linked by James Clerk Maxwell. The late 19th century was a period of rapid progress in electrical engineering. Thomas Alva Edison contributed in developing the commercial light bulb. Nikola Tesla contributed in inventing alternating current and many other things. These two even had a fight over DC and AC current, in which Edison did everything to stop commercializing Tesla's AC current, but now we use AC current for daily uses. In 1905, Albert Einstein published a paper that explained experimental data from the photoelectric effect. After the radio broadcasting started and television was invented, people started to use electricity for entertainment. With the invention of the first working transistor in 1947, a new era of electricity began, the era of electronics. The first transistorized computer was built in 1954. The first microprocessor was invented in 1971, and the development of personal computers started. In the late 20th century, people started using these modern devices for personal use. From 18th century to now, electricity was just an intellectual curiosity. Now it's like a basic need. We use electricity in everything, from daily uses to educational and medical uses. It has been possible only for those scientists and inventors who showed interest in this powerful natural phenomenon, without which we cannot even spend a day now.
So this is the short video of the history and definition of electricity. So I hope that you all understand the introduction to the electricity. So now I'll pass it for the next presentation. Thank you.
Good day everyone, I am Vishalini. My metric number is 277340. Now I will explain about model of atom, electric charge and law of conservation of electric charge. I attach some interesting videos on these topics so all of you can understand easier. I hope all of you enjoy the video.
Ants are busy building it. It takes many small grains of sand to make an anthill. If you take a closer look at the grain of sand under a scanning tunneling microscope, you can see that even the small grain of sand consists of millions of particles which are minuscule in nature. These particles are called atoms. Atoms are the building blocks of all material. Atoms are made up of three types of particles called protons, neutrons and electrons. An atom has a central nucleus with protons and neutrons in it. Protons are positively charged and neutrons have no charge, so the nucleus is positively charged. Protons and neutrons are collectively called nucleons. Electrons are negatively charged and are located around the nucleus. An atom has the same number of negatively charged electrons as it has positively charged protons in the nucleus. Therefore, atoms are electrically neutral.
Atoms can have different numbers of protons and electrons. When this happens, the charges do not balance. A positive atom occurs when there are more protons than electrons. Since there are more positive charges than negative charges, the atom has a positive charge. The result of adding the charges of both positive and negative particles is called the net charge. When one electron is removed from our neutral sodium atom, there are 11 protons and 10 electrons, one more positive charge than negative charge, giving the atom a positive charge.
Electrons are distributed in a definite path around the nucleus and are called shells or orbits. This concept was introduced by Niels Bohr. According to Bohr, different electrons revolve around the nucleus in their own different orbits. The atom has been compared to the solar system. In an atom, the nucleus is the sun and the electrons are the planets. Just like planets in the solar system, each electron revolves around the nucleus in its own different orbit. The orbits or shells are represented by the letters K, L, M, etc. The maximum number of electrons present in a shell is given by the formula 2n square present in the outermost shell of an atom are called valence electrons, and the shell which valence electrons occupy is called the valence shell.
Fact is the most important property of the protons and electrons. The charge is denoted by Q and the unit of charge is coulomb. Objects can be positively or negatively charged, hence Q can have both positive and negative values. The charge of a single electron or proton is known as elementary charge and is denoted with the lowercase e. Protons have a charge of positive e and electrons of negative e. This leads us to the law of conservation of electric charge, which says that you can't create a net electric charge. Instead, charge can only move from one place to another.
Hi everyone, I am Pavitra Manimaran. So now I am going to explain what is the function of force of attraction. Force of attraction is defined as a charged particles can be summarized as unlike charge attract and like charge repel. Below the picture shown that like charge repel is referred to two similar charge, for instance positive positive, and the below one is negative negative. The second one is unlike charge attract. It shows that opposite charge attract, which is one is the positive and another one is negative. Next, I will explain about three different charging, which is charging of solid object, charging by contact, charging by induction. For more understanding, I attached 3 videos regarding the charging of solid object, charging by contact and charging by induction in the next slide. So enjoy the video guys. The video is very interesting and I hope all of you understand well about this topic. Thank you.
As you rub a ruler with dry hairs, the electrons from the hair move to the ruler. Since the ruler is made up of plastic and plastic is a non-conductor of electricity, the extra electrons stays on the ruler. These extra electrons develops a negative charge near it. When the ruler is brought close to paper pieces, the electrons in the paper pieces gets repelled by this negative charge of the ruler. As a result, positive charge develops on the paper pieces on the ruler side, and thus the negative charge of rulers and positive charge of paper pieces attracts each other. Paper pieces, being small and light, gets raised up and gets attached to the ruler.
We're going to proceed with adding new ways to charge an object. Now, it occurs to me to clarify. So when we use the word charging in everyday language, we are almost always talking about a different phenomenon than I'm talking about. So how do you use the word charging most often in your everyday life? You're charging your phone, you're charging your iPad, you're charging your computer, right? That is actually not at all the same thing as what I'm talking about. We'll come back in probably another unit or 2 units to what exactly is happening when you charge your phone. But suffice it to say, you are not taking a bunch of positive charges and putting them on your phone, or taking a bunch of negative charges and putting them on your phone. Something else is going on. It does definitely involve pluses and minuses, but in a different way than we're talking now. Okay, right now we're just talking about transfer of pluses or transfer of minuses. And again, from the last video, we're actually always talking about transfer of electrons, transfer of minuses. But I will continue to treat them as if pluses and minuses can both move, just for simplicity. Okay, so charging by contact. This is really straightforward. So let's say my system is somebody else charged up a balloon. Okay, so here's my balloon. Okay, and it's got a bunch of negative charges on it. Let's say it has 5 negative charges. Okay, in reality, a more realistic number of negative charges might be like 5 times 10 to the 12th the negative charges, so a lot. But in any case, my system is me, I'm uncharged. Somebody charged this balloon up and then they sort of put it in this room with me. And now I'm going to come into contact with this balloon. So what do you think is going to happen? So I'm here, I'm going to come into contact with the balloon, and then let's say I'm going to take the balloon away again. I'm not rubbing it against myself, so I'm not doing any of that. I pick up the balloon and I touch it to myself, and then let's say I set it down again. So here's the balloon. Okay, what do you think I should draw in terms of charges in this diagram? Okay, so hopefully you thought about that for a minute, and there's a couple of good options. One, you might have decided that maybe all of the charges move from the balloon to the person. That's fine. Or you might have decided that some of the charges move. That's fine too. I'm going to say some of the charges move. So I have 2 minuses here. What should I draw now to make my diagram correct? Okay, now this is actually, you should be able to answer this based on the conservation of charge video. We have 5 minuses here inside our closed system, so we need 3 minuses on the person to make sure that the net charge, that charge is still conserved for this system. This is pretty straightforward. Charging by contact, you bring the balloon in, you bring any object in contact with another object, right? There's kind of a middle stage I'm not drawing here, which isn't great. But the middle stage is like the balloon is touching the person, and there are 2 minuses on the balloon, and 3 of the minuses leave and go to the person, and then this over here is your final diagram. So charging by contact, some object has a total charge, a certain amount of charge, 10 pluses, 7 minuses, and then it comes in contact with another object, and some of those charges transfer from one object to another simply by touching. Doesn't even need to be rubbing up against each other. They don't need to be different types of materials. This is probably the simplest type of charging, and I think it makes sense. You can almost think about charges like you'd think of an object covered in wet paint, right? You touch it, and you pick up some of the wet paint onto you. Or you touch an object that's charged, and you pick up some of the charges onto you.
Charging by induction. In the previous section we saw how a body is charged by friction. Let us now see how we can charge a metallic sphere by induction. Figure A shows an uncharged metallic sphere supported on an insulating rod. A negative charged plastic rod is brought close to the sphere. Free electrons in the sphere move away due to repulsion and piles up at the other end of the sphere. The near end becomes positively charged due to deficit of electrons. This distribution of charge ceases when the net force on the free electron inside the metal is zero, and this happens instantly. When the sphere is connected to a conducting wire, if it gets earthed and the electrons flow to the ground and the positive charge remains there due to the attractive force of the external charge. When the external conductor is removed, the positive charge remains in the sphere, making it a positively charged object. When the plastic rod is removed, the positive charge gets distributed uniformly over the sphere. Similarly, if a positively charged rod is brought closer to a sphere, the sphere acquires negative charge. Note: in this case, electrons will flow from the ground to the sphere.
A very good day to everyone. My name is Shankarasri Batumale, IGN number 281865, and I'm from group number 1. Today, as my part, I like to talk about insulator and conductor, semiconductor and Coulomb's law. Now, I like to give a short brief on what is insulator and what is conductor. Insulators are the material in which the electrons are not free to move through the materials. Example of good insulators are the glass, rubber, plastic, air and dry wood. So how about the conductors? Conductors are the material through which the electrons are free to move. Good conductors include silver, copper, gold and mercury. So guys, shall we see some activities that carry out to find out which object is insulator and which object is conductor? Shall we?
First, we have copper. Hook it up and yes, it's a conductor. How about this piece of plastic? Flip the switch, nothing happens. It is going to be an insulator. Now we move on to another piece of metal. It's aluminum. Flip the switch, and yes, it is a conductor. Now, how about some wood? Hook it up, flip the switch, nothing happens. So it is an insulator. After the block of wood, let's try this. How about we try a Sharpie? It's plastic, it's hooked up. We go to the switch and nothing happens. So it is an insulator. How about this? Let's try some water. I've got two nails hooked in. I flip the switch. Nothing happens. Well, let's modify the water slightly. Let's add some salt. As I add the salt, I pour it in. I go back to the switch. What do you think? Is it going to change? I hit the switch, and yes, it is now a conductor. The salt allows the electrons to move freely. Next, let's try this screwdriver. The reason why I use this, I have plastic on one end, metal on the other. I flip the switch, nothing happens. But now, if I move it to where it is touching metal only, it's now a conductor. So the plastic helps insulate it.
Wow, that was a great activity, right? So shall we go for our next part? So what is semiconductors? Semiconductors are material where there are a few free electrons and the material is poor conductor of electricity. As the temperature rises, electron breaks free and move through the materials. Example of elements which semiconductors are silicon, germanium and carbons. I think this is also find out something different, right? So shall we see some activities that carry out to find out how these semiconductors works especially in silicon object? Shall we?
When I fill this gap with a silicon wafer, the light stays off, so you might think the silicon's an insulator. But what if I heat it up? Thank you. It lights up. The silicon is insulating at room temperature but conducts electricity when it's very hot. It's a semiconductor whose conductivity changes based on the environment.
My last part from this presentation is about Coulomb's law. Coulomb's law states the 2-point charges exert force on another that is directly proportional to the product of the magnitudes of the charges Q and inversely proportional to the square of the distance R between their centers. Apart from the explanation about the Coulomb's law, there is also calculations formula which done by Charles Augustin de Coulomb. Now, let me watch through a simple video to learn the formulas and the calculation.
If two charged bodies are kept at a certain distance, they will experience an attractive or repulsive force depending upon the nature of their charges. If the bodies are charged by similar electrical charge, they will repel each other. If the bodies are charged by opposite electrical charge, they will attract each other. Suppose one body is positively charged with plus Q1 and the other body is negatively charged with minus Q2. The force acting between them is attractive. Again, one body is positively charged with plus Q1 and other body is positively charged with plus Q2. The force acting between them is repulsive. Again, one body is negatively charged with minus Q1 and other body is negatively charged with minus Q2. The force acting between them is again repulsive. The force is a vector quantity, which means it has direction in addition to its magnitude. Here the force acts along the straight line joining the centers of the charged bodies. Now, if you increase the charge Q1 keeping Q2 unchanged, the force is obviously increased. If you decrease the charge Q1 keeping Q2 unchanged, the force is obviously decreased. Similarly, if you increase the charge Q2 keeping Q1 unchanged, the force between them is again increased. If you decrease the charge Q2 keeping Q1 unchanged, the force is obviously decreased. According to Coulomb's law, force F between them is directly proportional to either Q1 or Q2, or in other words, F is proportional to the product of Q1 and Q2. Now, by keeping their charge fixed at Q1 and Q2, if we bring the charged bodies nearer to each other, the force between them increases. And if we take them away from each other, the force between them decreases. If the distance between their centers is r, it can be proved that force acting on them is inversely proportional to r square. It is also obvious that this force is not same for every medium. For example, if the bodies are kept in air, the force is different from the force while they are kept in water. Variation of force according to the medium is determined by a constant. Say this is K. Finally, we can say that force F equals Q1 into Q2 divided by K into R square. This is nothing but the expression of Coulomb's law. In SI system, force is measured in Newton, distance is measured in meter, charge is measured in...
I hope everyone understand about insulator, conductor, semiconductor and also Coulomb's law. Thank you everyone for listening and watching my video.
Hey, what's up you guys? Welcome to my session. and I hope you all understand what my previous members has explained to you. Now I'm going to give you guys some explanation and picturizations of electrical field. What is electrical field? Let's check it out.
If you imagine any charged object, it will always have its own electric field all the way around it. Just like masses have gravitational fields and magnets have magnetic field. To understand why this is important though, that's amazing that we have two particles, one with a positive charge and the other with a negative charge. Although you can think of their electrical field as diffuse area of influence all around them, in physics we show them with field lines, which are just lines with arrows on, and importantly, so they can go out of our positive particle but into our negative particle. The other thing to remember when you're drawing them is you have to draw them at right angles to the surface, so perpendicular like this. And if you are asked to draw them now, the strength of the field is strongest close to the particle, and it gets weaker the further away you get. So as charged particles get closer together, the electric field will start to interact more and more. If they are oppositely charged like our particles here are, then there will be attraction force between them, which can call an electrostatic force. Or in this, if instead though we had two particles of same charge, for example two positive particle or two negative particle, then the two particles will repel each other because alike charges repel. One last thing we need to cover is the strange interaction between electric fields and air. If we had an object that was really strongly charged like this piece of metal, then is having a strong electrical field all around it, whereas the nearby air particles would have no charge. In this state, air is an electrical insulator and can't conduct any electricity. However, in some cases, a strong electrical field like the one around a piece of metal can cause the surrounding air particle to lose electrons and become positive ions. We call this process ionization. And once has been ionized like this, it's able to conduct electricity, and this is how sparks are able to travel between objects.
Anyways, that's everything I've tried to sum up from chapter 1 for this video. So we hope you all find it useful, and we will see you soon again. Bye.